Hey guys, what's up? We're going to look at stationary waves. And we're in particular going to look at the difference between progressive waves and stationary waves and how we can form stationary waves. So a little recap, progressive waves. These are the waves that you've come across at GCSE and the waves that you most often come across in everyday life. They're always caused by oscillations and they have a net transfer of energy. So that's what makes them progressive. There is this net transfer of energy. And that's really important because when we see stationary waves, it's very different. And in this diagram, you can see that the oscillation is vertical and the wave on the sea, the water wave, is going at a 90-degree angle. So this, in this example, is a transverse wave. We know there's also longitudinal waves. And if you imagine this wave, this oscillation passing by these three boats, the motion of these boats is going to be vertical. They're going to each oscillate up and down, firstly A, then B as the wave passes it, then C. So all points along this medium are going to oscillate with the same amplitude. So all points will have the same amplitude of oscillation. And that's really important because it's very different to what happens in stationary waves. So just as a little reminder, there is a net transfer of energy and all points oscillate with the same amplitude. And as always with all waves, there is no transfer of matter or material. So what are stationary waves? Progressive waves transfer energy, but stationary waves, they've got this feature in which there is no net transfer of energy. And that's really important because that's really the defining feature of stationary waves. The energy isn't going anywhere. You can think of it as being stationary rather than progressing through space. And what's important to note, and we've got a picture here of a stationary wave. We draw it with a solid line and a dotted line to show the motion of this rope, and we'll look at that later, is the fact that certain points, labeled N for node, have no displacement. So they have zero amplitude. And there's other points labeled A, which are called antinodes, and they're positions of max amplitude. So this is really important that not all the points have the same amplitude as we had with progressive waves. So the second feature of stationary waves is that they have nodes and antinodes. And we'll look at more about how they form and what we mean by nodes and antinodes. So there's our differences. Stationary waves, no net transfer of energy, and they have nodes and antinodes. Let's have a look at how they form. So formation of stationary waves can be easier seen using just a rope, a person, and a tree. The person starts off with a vibration on the rope. So they start it here. And what they send out is a progressive wave, as we've seen, where there is a net transfer of energy. This wave is going to go along the rope and it will through the oscillation. And you can see here the progressive waves are continually being sent out. So we've got one progressive wave here and another one that's already been sent at an earlier time. So we keep on sending out progressive waves along this rope using the vibrations. You can see it going up and down here. This is a transverse progressive wave that's being sent out continually. But when those waves reach the tree, they reflect. And this is really important. So we've got incoming progressive waves, we get reflection, and therefore we've got waves traveling in two opposite directions. We've got the ones going forwards and the ones going backwards. And what actually happens to those is that they interfere. And it's really important that you use the word that the incoming progressive waves interfere with the reflected progressive waves. And now what we have formed is a stationary wave. It's almost the interference pattern of those two waves being transmitted and being reflected. This is the simplest stationary wave pattern that we can have on this tree, and we call this the fundamental. And I'll do another video, and it is on YouTube so you can see it, based on the stationary wave patterns that you can get when you change the frequency of this oscillation. But we always call the most basic, the longest wavelength stationary wave that can form the fundamental. So there we have it. We have a stationary wave now, which has got nodes, which are at the fixed points where there is no oscillation. And we have antinodes written with the letter A. And at this point, this particle is going to oscillate down, and then up with maximum amplitude. Other points will oscillate down and then up, but with a smaller amplitude. And if you go closer to the tree, the amplitude of oscillation of these points is even smaller. And at the node, there is no oscillation, there's no amplitude. So we have a stationary wave and there is no net transfer of energy. We have nodes and antinodes. So just to recap that once again, progressive waves are sent out. Then what happens is that they reflect and interfere with the incoming progressive waves, and we then get a stationary wave pattern being formed with nodes, positions of 0 amplitude, and antinodes, positions of maximum amplitude. Let's have a look at a few other examples rather than just a rope attached to a tree. We can see this in the lab, and we can use a mechanical oscillator connected to a signal generator, which just causes a tight wire to vibrate, and it's attached to a pulley at the other end and some masses. The masses just provide a little bit of tension in the string, and you can vary the tension and it will vary the stationary waves that you actually get formed. Once again, you can see the progressive waves are being sent out, and this happens continually. So you must keep on sending progressive waves out, but then when they reach the pulley, they reflect. And when the reflected waves interfere with the incoming progressive waves, we get our stationary wave pattern being formed. Once again, you can see that this is the fundamental. It's got the longest wavelength. But if we were to increase the frequency of this oscillator, we could get what's known as the second harmonic, which is the next stationary wave pattern formed. And you can see it's got an extra node. So it's got a node at the ends where it's fixed. We've got some antinodes here. Whereas in the fundamental, we just had 2 nodes and a single antinode here. So that's another example of stationary waves being formed. People who play panpipes or any musical instrument really is based upon stationary waves. So panpipes are these little wooden pipes, and people blow across them and it makes a lovely noise, a lovely sound, and the different tubes in the pan or the different pipe creates a different musical note. So let's have a look at how the stationary waves form here. When someone blows across the top of one of the pipes, sound waves are transmitted down. So that's our progressive wave, and it's a sound wave being transmitted down. And when this sound wave reaches the end of the pipe, it actually reflects. It reflects off the bottom. And when this progressive wave that's going down the tube interferes with these reflected waves, we get a standing wave pattern. And you can easily see why we get different notes. The tubes have all got different lengths. So because they have different lengths, we get different fundamental wavelengths. So this one has got a long wavelength here, and this one's got a short wavelength. So this will be our low pitch or low frequency, and this will be a higher frequency note, a higher pitch. So really important, we always say progressive waves are sent out, the progressive waves reflect and interfere with the incoming progressive waves and form a stationary wave pattern. This actually happens in your kitchen as well. So you've probably got a microwave in there, but microwave ovens work using stationary waves. Inside a microwave oven, you've got a microwave emitter, which continuously emits microwaves, you can see here. And the inside of the oven has got a metal casing. The metal causes microwaves to reflect. So the progressive waves are sent out, and when they hit the metal, they reflect. So we've got incoming progressive waves and reflected progressive waves, and when they interfere, we get a stationary wave pattern. I've not shown the fundamental here. I've shown a different harmonic in this oven. And you can see there's areas where there's nodes and there's areas of antinodes where they've got maximum displacement, maximum amplitude. The antinodes are actually really important in a microwave because they're the positions where you've got the greatest amplitude. And you should know that the intensity is proportional to the amplitude squared. Therefore, if you double the amplitude, the intensity goes up by a factor of 4. So the areas of the antinodes is actually where you get the most intense microwaves, and that's where your food cooks the quickest. And that's why the plate on a microwave has to rotate so that the food is continually going in and out of these antinode areas, and you get a more even cooking rather than just cooking at those specific antinode points. So really important. This is just another example of how stationary waves are formed. So let's have a look at a summary. First of all, progressive waves, they're the waves you're normally used to. That's where there is a net transfer of energy from point A to point B. And all points experience the same amplitude of oscillation as the wave goes past. So each of these boats vibrates up and down with the same amplitude. But when we look at stationary waves, there is no net transfer of energy. In fact, energy is stored within the system. And that's because waves are being sent out and they're being reflected. Different points experience different amplitudes. And there's 2 words that you must be aware of. Nodes are positions of 0 amplitude, where the waves, when the reflected and incoming progressive waves cancel out destructively, they form nodes. And antinodes are positions of maximum amplitude, which is where the interference pattern is constructive and we get maximum amplitude and maximum intensity of oscillation. And all stationary waves form in the same way. So it doesn't matter what example they give you in the exam, you say these sentences. Progressive waves are sent out. Then the progressive waves reflect and interfere with incoming waves. And then you form a stationary wave, which has nodes, positions of 0 amplitude, and antinodes, positions of maximum amplitude. We've looked at it on a rope, we've looked at it on a wire, we've looked at it in microphones and in pan-pipes. There's many different examples, but the description is the same each time. That's it. Thanks for listening. See you all soon.